All right. So we're starting a new chapter today, and this chapter is on centroids, center of gravity, center of mass. They're all related topics. So there's several reasons why we'd want to find the centroid. One is we want to find out where to put the weight force on various shaped components of machines and frames. So we'd want to find the centroid for that. The other reason is related to the last chapter when we were doing shear and moment diagrams. And if you remember, we looked at the tables and they had deflections on them. And we didn't calculate the deflections because we needed two more quantities we haven't discussed. One is the modulus of elasticity, which is part of another course. And the other is the moment of inertia, which is the next chapter. In order to calculate the moment of inertia, for those beam deflections, we need to take the moment of inertia about the centroid. To take the moment of inertia about a centroid, first thing we have to know is where is the centroid. So that's another reason for calculating these centroids related to statics. So as long as the shape is regular, rectangular, triangular, round, parabolic, we can calculate the centroid fairly easily from tables. If we have an irregularly shaped object, such as this blob here that's shown in the graph, then we're going to have to use calculus. So we would divide up the body into an infinite number of particles of differential size. So that's this little cube here is differential size, and it would have a gravitational field on it that would be dW, a differential weight. The weight of the body then is the resultant of the gravitational force on each particle and will pass through a single point called the center of gravity G. So G is shown on the next diagram, where all of those little dWs are replaced by a single force W through the center of gravity G. The location of the center of gravity can be found by taking moments about the X, Y, and Z axis. After we've taken the moments about the X and Y axis, the equivalent moment would be achieved by placing this force at the point G, which is, each of the individual dWs, go back up to here, would be at a value x tilde along the x-axis. This little curly on the top is called a tilde. So x tilde along the x-axis, y tilde along the y-axis, and z tilde along the z-axis. So we would integrate to find moments about the x-axis for all of the little dWs, so all of the little x tildes, the distance from the x-axis. Sorry, that would be y tilde would be the distance from the x-axis. And then we would find our resultant moments by integrating. So x, the resultant moment would be the sum of all of the moments about the axis. This is shown for the y-axis. And then we're going to replace that moment by the x bar, which is the centroid location, times the weight, because that would be the moment about the y-axis. So x bar w equals the integral of x tilde dw. I don't know why I've got a blank page here. So then we can find the location of the center of gravity by taking these two integrals and doing division. So x bar would be x tilde dw over dw, y bar would be the integral of y tilde dw over the integral dw, and z bar similarly. So that'd be the center of gravity. The center of mass, what's the difference between the center of mass and the center of gravity? Yes, this is integrated with respect to mass instead of weight. They're almost always going to be exactly the same point. The only time that it would be different is if it's not in a uniform gravitational field. So if we were looking at the center of weight of the moon orbiting the Earth. I mean, I guess the Earth's gravitational field would be slightly different on the farther side of the moon, so we could take that into account. But even at that, it's going to be virtually the same location as the center of mass. So in a uniform gravitational field, the center of mass and center of gravity will be the same point. And most of the time, we can actually just find a center of volume, as long as the material is uniform. So as long as the machine part we're trying to find this center of mass or center of gravity of is the same material, then we can just find a center of volume. If it's a composite part, then we would have to integrate with respect to mass and take the density into consideration. That's what this is saying here. So if the material is homogeneous, then the density will be constant and the center of volume will be the center of mass. In other words, rho will cancel. All right. We don't always have to integrate with respect to volume. If we have a plate or something of uniform thickness, then we can integrate with respect to an area. And sometimes that's going to be easier. So if we're integrating with respect to the area, then we're only going to have two terms, because there's only two dimensions to the area. So if the area is in the xy plane, x bar is the integral of x tilde dA over the integral dA. And these are all basically the same formulas. Centroid of area is also going to be important when we're doing our moment of inertia calculations. So that's not to find the weight or where the weight applies, it's to find where the neutral surface is on the cross-section of whatever the beam or post happens to be, structural member. So if the area lies in the xy plane and is bounded by the curve, then its centroid can be determined by integrating with respect to x or y. So here's the centroid C here, and we could find this centroid by integrating, this is integrating with respect to x. So we would have our areas here that would be y times dx. And if we integrate with respect to y, then the area would be dy times x. So it's either y dx or x dy. How do you decide which one to integrate? That's exactly the right answer. So the answer was whichever one's easier. I can find x bar and y bar integrating with respect to x, and I can find x bar and y bar integrating with respect to y. I don't have to do the same integration to find both of them, but I should always choose the one that looks like it's going to be the easiest. And sometimes the one that looks like it's going to be the easiest, you'll run into a problem. You get something that's difficult to integrate. Try integrating with respect to the other variable. The only thing to note on here is if we're integrating with respect to x, then the centroid of this differential, it doesn't look differential, but we can imagine that this is a differential sized element here. The centroid of this, x tilde, is x. The centroid with respect to y, or sorry, the y centroid when we're integrating with respect to x is y over 2. Because this has no thickness. So its center is at its location, which is x. The y centroid does have dimension, so it's going to be at y over 2. When we integrate with respect to y, the y centroid of the differential area is just y, and the x centroid is x over 2, x being a function of y. Have to remember that. All right, and the last type of centroids that we're going to calculate looks like it should be the easiest. It's a little bit misleading because it's actually going to be the most challenging integrals that we're doing, and that's to find the centroid of a line. So you'd want to find the centroid of a line if you've got, say, a piece of wire or a piece of metal rod that's bent into some kind of a shape to support other parts of a machine, or even if it's just an ornament as part of the machine. Industrial designers like to put things on there that do nothing but look good. So if we want to find the centroid of this line to figure out where its weight is acting, then we would integrate with respect to the length along the line. So x bar would be, so we're integrating along this length here, and each differential part of the length is going to have an x tilde and a y tilde. So the moment about the x-axis for this differential point would be x tilde times the length, because it would have a uniform mass per unit length. And then we would add up all of those moments, and then we would divide by the entire length of the wire, or whatever the piece is. So if the line lies in the xy plane and can be described by the curve y equals f of x, then the length of the differential element dl can be found by the Pythagorean theorem. So the length of this dl, right, this is a right triangle here. So dl squared equals dx squared plus dy squared. So that gives us this handy differential. If we're going to be integrating with respect to x, then we would take the dx to the outside of the radical, and we'd multiply, we'd divide the dy squared by dx squared, so that we can also factor out the dx here. So we end up with a function here with a dx on the outside. If we're integrating with respect to y, then we'd factor out a dy and put it on the outside of the radical. All right, before we do some examples, there's some important points to consider. First of all, the centroid of a line, area, or volume represents the geometric center of the body. It will only be the center of mass and center of gravity if the material is homogeneous and there is a uniform gravitational field. If that's the case, we're good to go. If that's not the case, then we'll have to put the varying density into, and the varying gravitational field into consideration, or into the integrals. The formulas for center of gravity are simply the balance between the moments of the resultant force and the sum of moments of all of the system. That's the basis for those formulas, and that's all that we're finding. Where we can put a single force that's going to have the same, not only have the same force as all of the forces, but the same resultant moments. And finally, the centroid can be located at a point that is not necessarily on the object. For example, the centroid of a ring or of a hollow sphere, or any of those bent wire shapes, it's probably not going to have a centroid that's actually on the wire. All right, and here is our first example, which is a bent wire. Just zoom out a little bit so we can see the whole problem. So it says the uniform rod is bent into the shape of a parabola and has a weight per unit length of 6 pounds per foot. Determine the reactions at the fixed support of A. So, first of all, what components of reaction can we have at the fixed support of A? Right, we can have two components of force and a moment. It's a fixed support, so it takes away all of the degrees of freedom. So draw those in AY, AX, and then we'll draw in a moment about A. Okay. And what forces are these reactions constraining? Just the weight. Right, so we would draw a weight, force. I don't know exactly where the center of mass is. I can kind of guess that it's going to be somewhere close to the center here. All right, that down there. So that's W, and that's going to be a distance x bar away from the y-axis. I don't really care what y bar is because the weight's going to go through every point that's x bar away from the y-axis because the gravitational field is along the y-axis. So I'm not going to draw that in there. So there's our free body diagram. What do we need to find first? I don't know the magnitudes of any of these forces. All I know is that this bar has a weight per unit length of 6 pounds per feet. So if I can find the length of it, then I can find the weight of it. So the first thing we'd want to do is find the length. I'm just going to put in brackets and weight. The rod. So how are we going to find the length of the rod? Right, we're going to do the arc length formula. So which basically says L equals the integral of dl. And the integral of dl can be either of these two. Well, it's both of those two, but we can choose either one depending which variable we're going to integrate with respect to. Which variable do you think it's going to be easier to integrate with respect to? Okay, if we try to integrate with respect to x, then I'd want to rewrite this as y equals f of x. So if I write this as y equals f of x, that would be y equals root 3x. That was easy. Okay, and then our integral dl would turn into the integral of the square root of 1 plus dy dx dx. Yes, thank you. Okay, and that would go from 0 to 3. What's dy dx? The root 3 is a constant, so the root 3 is going to stay there. And I have x to the 1/2, so if I take the derivative, I'm going to end up with x to the negative 1/2 and then I have to multiply by 1/2. So root 3 over 2 root x. Oh, this is looking absolutely wonderful. So fortunately we square that in this term here. So this would become integral from 0 to 3 square root 1 plus, there's going to be 3 over 4x. dx. Okay, now what? Does anybody know how to integrate this formula? Okay. So at this point you could try and find it in tables, and hopefully you can. I don't have the tables with me. Or we can try integrating with respect to the other variable. If you get to something you can't integrate, try the other variable. So this is y as a function of x. Let's do x as a function of y on the other side. Let's switch colors. So if I want to write this equation with x as a function of y, all I need to do is divide both sides by 3. So x equals y squared over 3, and then dx dy y over 3, well, 2/3 y. Okay, so then our dl, L equals integral dl equals the integral 1 plus dy dx squared, so that'd be 2y over 3 squared, or 4y squared over 9 dy. All right. How is that not the same as that? Oh, it is. Okay. Anybody know how to? Well, what I would do in this case, again, with either of these, I'd see if I could find it in integral tables. So in your textbook, there's integral tables on page 601. And I'll tell you that there's one of the tables that fits. It fits this one. So C integrals in Appendix A. So one of the integrals that we're given is the integral of square root of x squared plus or minus a squared dx equals 1/2 x square root x squared plus a squared plus or minus a squared ln x plus x squared plus or minus a squared plus or minus plus c. Always plus c. So all we have to do is make this look like this. So I've got a y squared term in here, so I want to have the y squared term by itself. So how am I going to get rid of this 2/3 in here? I could, or I could just factor out a constant. Right, because this is a 2/3 squared, so if I factor out a 2/3, constant, integral, square root, switch the order there, so that's going to be y squared. I factored out a 2/3, so this is going to be a 3/2 squared now. Let me just show where that's coming from. So this becomes this. Okay, does everybody see that this is the same as this? Okay, and this matches up with this. So I'm going to integrate this. My variable of integration isn't x, it's y. And my value of a is 3/2. So that's going to be, oh, and we're still integrating between 0 and 3. So that's going to be 1/2 x, or sorry, it's not x, it's y. Y root y squared plus 3/2 squared, so 9/4, plus a squared, it's going to be 9/4, on y plus root, that should be a squared there too, y squared plus 9/4. And we can forget about the plus c because we're evaluating that between the limits of 0 and 3. Sorry?
Like your 2/3 and you have.
Oh yes, the 2/3 should still be here as well. So 2/3 times that is, instead of it being 1/2, that should be 1/3 then. Thank you for catching that. Okay, and because we're evaluating between 0 and 3 then, that's going to be 1/3 so when y equals 3, that's going to be 3 root 3 squared plus 9/4, so it's 9 plus 9/4, that'd be 45/4. plus 9 over 4 ln 3 plus, that's still going to be root 45 over 4. And then we're going to subtract the value of this at 0. When y equals 0, the first term disappears, but the second term doesn't. So it'd be 9 over 4 ln, and that's just going to be root 9 over 4, which is 3 over 2. Anybody else? All right, I've got one answer, 4.44 feet. Does anybody have the same? Okay, so another one confirmed. Anybody have anything different? Okay, so before, I'm going to write it down, 4.44 feet. Let's just have a look at the problem and see if that makes sense. If this was a straight line diagonal, how long would the rod be? Now, if it's a straight line diagonal, it would be 3 times root 2. So it's bent, so it's going to have to be longer than 3 times root 2. What's 3 times root 2? .24. So it is. It's a little bit longer than a straight diagonal. So that makes sense. That's also the same answer I got last year. So we're going to go with that. 4.44 feet. So here, our integral with respect to x, we ran into a dead end. So we write in here, try with respect to y. And then integrating with respect to y, we were able to do it with the integral tables. I don't know. I didn't try it with respect to x last year. I just tried it with respect to y, and then I know I have the one I looked up in the table. There might be. And it'd be the same kind of thing where you have to just manipulate the values in here by taking out a constant until it looks like something that's in the table. So usually they'll have the x by itself. So it might have been 1 over x plus a. If it was in the tables. I'm not even sure that it would have been. Okay, so once we have the length, then we can go our weight is equal to L times the density with respect to length. So actually, let's just put in the values here. 4.44 feet. And then we had 6 pounds per foot. £26.6. All right. Now we need to find out where that weight is acting on the rod. So how are we going to find x bar? So to find x bar, we would go back and use this equation. And we don't have to integrate with respect to y this time, or x. We can integrate with respect to either variable. If we integrate with respect to y, then we have to remember that x tilde is going to be, well, x tilde isn't going to be x over 2 this time, because it's a length. So x tilde would just be x. So our centroid is equal to the integral of x tilde dl over the integral dl. We're not going to integrate dl again. We know what dl is, or we know what the integral dl is. We will have to integrate this one, though. So if we try integrating with respect to y again, then we already know what our dl is with respect to y. And our x tilde is going to be what? X tilde is going to be x here as a function of y. So at each of our dy's, the x tilde is going to be y squared over 3. Y squared over 3, and then our dl is the same as it was before. I'll put it in the simplified form, 2/3 root y squared plus 3 over 2 squared dy over, well, we know it's 4.44 feet. All right. So we can simplify this a little bit. We can take a constant out. The 2/3, and the y squared over 3 is going to come out as a 2 over 9. 2 over 9 integral y squared root y squared plus 3 over 2 squared dy all over 4.44 feet. Does anybody know how to integrate this one? I know you guys are doing integration techniques, and you probably have ideas of how you could integrate it using various substitutions and trigonometric. That would be time consuming. So in an exam, I suggest that you not do that, but you flip to Appendix A in your textbook, because it is an open book exam, and see if you can find something that matches this one. And there is in Appendix A, and unfortunately this one's a little bit uglier than the last one. So from Appendix A, the integral of x squared root x squared plus or minus a squared dx equals x over 4 x squared plus or minus a squared to the 3 over 2 minus or plus a squared over 8 x root x squared plus or minus a squared minus a over 4 over 8, sorry, a to the 4 over 8 ln x plus root x squared plus a squared plus or minus a squared plus c. A little uglier, but not really that bad. So we're integrating so the integral, I'm just going to take this integral out here, y squared root y squared plus 3 over 2 squared dy between 0 and 3 is going to equal y over 4 y squared plus 3 over 2, actually we can square that, plus 9 over 4 to 3 over 2 minus, I've got a squared, which is 9 over 4 divided by 8. So what's 9 over 4 over 8? Nine over 32. 9 over 32 y squared plus 9 over 4 minus, now I've got a to the 4, so that's going to be 81 over 16 over 8. What's 16 times 8? 8 times 8 would be 64, times 2 would be 128. 128 ln y plus root y squared plus 9 over 4 and that's all going to be evaluated between 0 and 3. We have 30.9. Anybody else calculate the integral already? Okay, so I'm going to wait till at least one other person has a value. Take that 30.9 and then that's just for the integral. Multiply by 2 over 9 and then divide by 4.44. What do you get?
1.55.
That's not right. It's got to be less than 1.5. Yes, it is so long. That's why I'm not writing it out with all the numbers substituted in. When you do the y equals 0, you do only have to do the last term, right? Because each one of the other ones has a y term in front of it. But for y equals 3, you need to do all 3 terms. What have you got? Oh, okay. Do you want a pen? For the integral? Or for the whole? Oh, and then divided by 4.44? So what do you get for x bar? Okay. So we're getting different values here, and that's not uncommon. If we look here, the bent wire goes between 0 and 3 feet. The first half is more vertical than the second half. So there's more wire on this side than there is on this side. The centroid is going to be less than 1.5. If it was a diagonal, it would be right at 1.5. All right. So Michael, what did you get? 1.23. Okay.
I got 1.20.
Okay. It's somewhere around there, 1.20, 1.23. Last year we couldn't, it's such a long calculation. We had 5 different values that people were getting because 5 different people were calculating it. And 1.20 was the one we chose because it was in the middle. 1.23 was also one that people got. So we're going to go with 1.20. So if our calculator is correct, we get something around and the exact value isn't important in this point, in this place, because if you're doing this on the exam and you've got all of these terms in here and you put in all the values, that's the important thing. And if you made a calculation mistake, you're going to lose like a half a mark. So 1.20 feet. So if we use 1.20 feet, so we'll assume that's correct for now, then what's our next step? Right, now we can do the equations of equilibrium. So we're doing the equations of equilibrium for the rod. And start with net force in the x direction equals 0. What forces are acting in the x direction? Just AX. So AX is going to be equal to 0. Net force in the y direction equals 0. What forces are acting in the y direction? I've got AY, yep, and the weight, which we know is 26.6 pounds. So AY minus 26.6 pounds. So from this one, we have AX equals 0. AY equals 26.6 pounds. And our last equation of equilibrium would be the moments about A equals 0. One of those moments is the couple moment that we drew in there, so MA. What else is going to produce a moment about A? Okay. The weight times the X bar. Minus 26.6 pounds times 1.20 feet Therefore, MA equals 32.0 foot-pounds. So that problem that looked the easiest is actually the hardest one when we're integrating with respect to length, because we end up with that radical that's going to be part of our integral no matter what variable we integrate with respect to, and unless we can match it to some of the patterns in our integral tables, it's going to be very challenging. It's actually somewhat easier to do something like this, even though this looks uglier. So this time we have a plate which has a thickness of 10 millimeters and is made of steel having a density of 7,850 kilograms per meter cubed. And we want to determine the horizontal and vertical components of the reaction at pin A and the tension in cable. Let's skip a page here. I have another problem in my notes. Oh well, we'll do this one. Okay, so the plate has a thickness of 10 millimeters, made of steel. Determine the horizontal and vertical components of reaction at the pin and the tension in cable BC. So to find those, we should do a free body diagram. What forces are acting on the plate? The reactions at A, so there would be hinge joint, it's going to be an X and a Y, but no moment. And the tension in the cable BC. And wherever the center of gravity is, there's going to be a weight. So label those. That's AY, AX, call that TBC, tension in BC. Or I could call it FBC as well. Doesn't matter. And the weight. And the weight is going to be acting at the centroid. So this one's actually similar to the previous one in that we're going to have to find the weight and the centroid before I can solve for the equations of equilibrium. So what should we find first? Center of mass, yeah, but actually in this case the center of mass is going to be located at the center of area. And that's not the first thing that I want to find anyway. Because in order to find the center of area, I'm going to need to find the area. And in order to find the mass and the weight, I'm going to have to find that area as well, and then multiply by the thickness and the density. So the first thing we're going to want to do is find area, and from the area we can find the volume and the weight. And then our second step would be to find the center of area, which is going to be our center of mass, our center of gravity. then our third step is going to be to solve the equations of equilibrium. All right, so if our first step is to find the area, which variable do you want to integrate with respect to? You want to do y? Okay. If we're integrating with respect to y, then we would need to have x as a function of y. So how would I take this relationship and write x as a function of y? Divide by 2. That's easy. So x equals y cubed over 2. That's the equation of the curve. If we're integrating with respect to y, though, we have to be careful because our area isn't right next to the y-axis. So our differential area would be here. This is an exaggerated fat differential area. So the length of it is going to be 4 minus x. And the centroid of it is going to be halfway between here and the 4. So that would be 4, so we're going to find that distance. That's going to be x plus half of this. So the x tilde is going to be x plus 4 minus x over 2 to get to the center. And that's going to be x over 2 plus 2. Okay, and this is our dA equals x dy equals, sorry, it's not x dy, it's 4 minus x times dy. 4 minus y cubed over 2 dy. Alright, so to find the whole area, we're going to integrate that between y equals 0 and y equals 2. Fortunately, we got a nice polynomial function, so we can integrate that. The antiderivative of 4 is 4y. The antiderivative of y cubed over 2 to the 4 over 8. We're going to evaluate that between 0 and 2. And at 0, both of those terms are 0. So we really only have to evaluate it at 2. So 4 times 2 is 8 minus 2 to the 4, which would be 16 divided by 8, 2. So this was 8 minus 2 equals exactly 6. Does that seem to make sense? Well, if this was a rectangular plate, it would be 8 meters squared. So we're missing about a quarter of the material for changing it to this cubic shape. That looks reasonable. So we can assume we haven't made any mistakes. Once we've found the area, then we would go to find the volume, because we know that it's 10 millimeters thickness. Yep. Just lost content? Okay, just let me get it back. Let me try to get it back. Oh, no, it's gone. Okay, just a second till Campbell River comes back. Oh, there. Okay, thanks. So we've got the area times the thickness, which was 6 meters squared. 1 centimeter would be 0.010 meters, or 10 millimeters, I think was what was given. So that gives me 0.060 meter cubed. And then we can calculate the weight from that. Weight is equal to the mass density, which was given, times acceleration due to gravity, times the volume. So 7,850 kilograms per cubic meter, 9.81 meters per second squared, and 0.060 meter cubed. $4,621 newtons. All right.
Dennis.
Yep.
Can I ask just a little DA calculation on the graph? You got the 4 minus x by substituting the height of the plate into the x equals y cubed over 2. The minus in there.
Okay. So the x equals y cubed over 2 is just giving me the left edge of the plate. So the plate goes from there to 4. So the length of it is 4 minus y cubed over 2. Right? So we're not doing the x parabolic area over here. We're doing this area on the right side. Okay, and that's a good reason for actually always drawing your differential area, so that you remind yourself that you're not actually taking this area here, and you're not looking for the centroid of this. You're looking for the other side of the function. All right. Sometime 35. So we found the weight. Now we want to find x bar. So how are we going to find x bar? So step 2. X bar we know is going to be the integral of x tilde dA over the integral dA. Okay, we've already done the integral in the denominator. We could switch variables of integration, so we could integrate with respect to x instead of y, but that's probably not a good idea. Actually, in this problem, it's not going to be that difficult either way. We're going to end up with polynomial type functions either way. But if we stick with integrating with respect to x, we have x tilde here as a function, sorry, integrating with respect to y. We have x tilde as a function of y, or we almost do. So that would be y cubed over 4 plus 2. So that would be the integral y cubed, y cubed over 4 plus 2. Let's start that all over again. Times my dA, which is the same dA we had before, 4 minus y cubed over 2 dy. Integral dA, I know, is going to give me 6 meters squared. All right, what do we do with this? Expand it. Is there anything you'd like to do before we expand it? Okay, we couldn't remove a common factor. What factor would that be? So you want to remove a 2 out of both of them, or out of one of them? Or we could just expand it. If you take a factor of 2 out of this one, then you would see that expanding this is going to give us a familiar pattern, because this binomial is it's kind of the complement of this binomial, only it's multiplied by 2. So it's going to give us a difference of squares. If we don't see that, then we'll just FOIL them out. We're going to get the same answer anyway. So if we FOIL those out, we're going to have y cubed over 4 times 4, which is going to be y cubed. We're going to have y cubed over 4 times y cubed over 2. Y to the 6 over 8. And then the inside is going to give me a plus 8. And the last is going to give me 2 times negative y cubed over 2, which is the minus y cubed. So we can see those y cubed terms are going to disappear. And the integral is from 0 to 2. So that's going to be the integral of 8 minus y to the 6 over 8 dy, 0 to 2 over 6 . So antiderivative of 8 is going to be 8y. Antiderivative of y to the 6 over 8. Y to the 7 over 56. Between 0 and 2, again, all over 6. You don't have to evaluate it at 0 because all of the terms are 0. Just evaluate it at 2. .29 meters. Again, we'll have a look at the diagram. Does that make sense? It does, because it's on the right half of the plate, and we've cut away much more of the left than the right from the rectangle. So that seems to make sense. All right, so we've done step 1 and we've done step 2. All we have left is step 3. And we're going to need a new page for that. So our equations of equilibrium, let me just copy that over. So our equations of equilibrium, first of all, net force in the x direction is only ax again. So that component of the pin support is 0. Net force in the y direction equals 0. I've got 3 forces in the y direction now, so that's going to be AY plus the tension force, TBC, and then I've got the weight. And the weight we know is 4,621 newtons. 4,621 newtons. Okay, 2 unknowns, can't solve it. So what do we need for our third equation? Well, we could do moments about any point, but A would be a good choice. And which forces are going to produce a moment about A? Right, so TB is our positive moment. It's a perpendicular distance of 4 meters away. So that's going to be 4 meters TBC. And then the weight is going to have a negative moment, and it's 2.29 meters away. And it has a magnitude of 4,621 newtons. So from that we can calculate TBC. 2641 newtons. Two 641?
Yeah.
I have 2646 written here. But we'll go with yours. 2641 newtons. And then from there we can calculate AY. 4.5 or 4.6?
4.5.
Okay. I'm going to go with 4.6 then. Majority rules. And that's what I have from last year. It's going to vary slightly depending whether you rounded this to 3 digits, which is what we've got written down here, or you kept the numbers in your calculator. But okay. And really we should be giving these to 3 sig figs anyway. So if that's 2646, then FAY is 1,975. That'll be more if this one's less. All right. So our next example is finding the centroid of a volume. But fortunately, there's a high degree of symmetry for the volume. And we're going to want to find the centroid, so we're going to want to find x bar, y bar, and z bar. But two of them are going to be reasonably easy. Extremely easy, actually. So locate the centroid of the homogeneous solid frustum of the parabola. Start that again. The centroid of the homogeneous solid frustum of the paraboloid formed by revolving the shaded area about the z-axis. So the shaded area is between the z-axis, and if we look at it on the y-axis, this would be h over a squared times a squared minus y squared. So h would give us, h is the total height, and this has been cut off at h over 2. All right, so let's start with x bar. How are we going to find x bar? Method of staring, or we could say by inspection, or obviously if it's rotating about the z-axis, its x bar and its y bar are both going to be 0, because there's equal amounts of the solid on the positive x-axis and the negative x-axis, and the positive y-axis and the negative y-axis. So right on here by inspection. X bar equals y bar equals 0. So that means we only have to find z bar. How do we find z bar for a volume? Well, z bar is equal to the integral of z tilde dv over the integral dv. What variable are we going to be integrating with respect to?
Have an equation with y is equal to y.
No. We're not going to integrate with respect to y because my z tilde would be very difficult if I'm integrating with respect to y. We would want to integrate with respect to z. So what we'd be looking at is we're not going to have time to finish that right now, but I will have time just to draw in our differential volume. If we're integrating with respect to z, is going to be a circular area of differential thickness. So this thickness here is exaggerated. That's going to be my dz. And the volume is going to be this area times dz. All right, so we are out of time. So we'll finish this problem next time, and then the next part of the chapter when we're looking at composite bodies is actually going to be a lot easier. And for most applications it's more applicable because we don't usually have these odd-shaped, we don't have that many of these odd-shaped pieces in a machine or a framework. We're going to have regular shaped pieces, cylindrical pieces, rectangular prism pieces. But we still have to know how to put all of those together. If I'm welding together a bunch of pieces of square plate and angle iron and rectangular prism, I still need to find the centroid. But we don't have to use calculus. All right. Scroll back up to the first question. This one?
Yeah. Just down to the second.
Down to the second page. Okay. I will post the notes so you can double check the calculations. And actually, I should check them myself.
No, mine was 1.2. That mine is the exact same number you got.